I would like to start this session on treatments and therapeutics. Obviously, this follows on really neatly from the previous session, and we're really taking forward the challenges and in terms of what happens once poisoning has occurred. And whilst we are obviously looking at preventing poisoning, we have to consider the fact that it actually does happen. I would like to introduce Professor Andrei Abramov, who is the Professorial Research Associate at the UCL Institute of Neurology here in London. Andrei has a broad scientific interest with a major focus in the interrelationships among calcium signaling, mitochondria, and free radicals, and in the contributions of mitochondrial dysfunction to disease pathogenesis. That might all be a bit of a mouthful for all of you here. Indeed, it didn't slip off the tongue. But what you'll see from Andrei's presentation is that he has great expertise in the area of cell physiology and the role of mitochondria and oxidative stress and protein misfolding in particular Parkinson's disease, Alzheimer's disease, and other diseases that we will see today. So without further ado, I will hand over to Andrei, who has, I will say, because I have had a bit of insight, developed something that will interest everybody in the room. So listen carefully. Thank you.
Yes, thank you for introduction and inviting me to present our work, actually, which is funded by CORD, previously Gas Safety Trust, and it's just yes. My presentation is neuroprotective strategies to improve treatment and outcomes, but in reality, we cannot say about any treatment and about any strategies without understanding the mechanism, how generally all this pathology started. And if we look at what is in the literature, at the moment, it's that from neurological point of view or psychiatric, that 67% of survivors of the carbon monoxide poisoning have severe neurological or psychiatric problems. And if you, for example, speak with a neurologist, what I was surprised that, all of them know what is it, and know how big a problem, but at the same time, research in this area, I would say pretty low, because even if you look in some databases on the publications on carbon monoxide, the vast amount of the publications will be about how good is a carbon monoxide, which is good, that area is developing, but that relatively small amount of the publications in the explaining what's going on with toxicity of carbon monoxide. But the classical is just a distribution of the infarct core and how it damaged the brain. But again, what is coming to, for example, I'm a relatively new person in this research field, and what I can say that, of course, then we just came to that. It was several questions. What is actually carbon monoxide known to do? And it's first, of course, it's already been mentioned that it's induced formation of carbohemoglobin, which is let's say, preventing delivery of the oxygen to the tissue. So, well, we induce hypoxic and probably even anoxic condition in the tissue. What is mostly consume all this oxygen in the tissue is it's predominantly mitochondria, which consume it for generation of the energy in the form of ATP. And what is important, and it's very important, that it's shown that it's also inhibit mitochondrial respiration, our cellular mitochondrial respiration, well, the final point of the oxygen consumption in our body. And that, again, well, it's a question, about what we can do with this knowledge, but this is a mitochondria generally, and it sounds, very far from school course, whatever, but what is important, I just like to point several major points which is relevant to physiology, pathology. First, this is a mitochondrial respiratory complexes or electron transport complexes where oxygen is consumed, but production of ATP, participation in the calcium transport, but it's not only. This mitochondria is it's the last point before the cell death is started. When this pore, which is called permeability transition pore, opens, we cannot stop the process of the cell death, which is in many other cases, in our body is fine, because, we have constant renovation of our cells, but it's not very good in our brain, where because neurons is a post-mitotic cells, they're not produced later. And that's how mitochondria looks like, it's a human neurons, because mitochondria produce it due to ATP through the maintenance of this mitochondrial membrane potential, and we can visualize it. When we induce chemical hypoxia, which is when we blocked mitochondrial respiration in our cells and ATP production, and we can see that mitochondria are completely depolarize. If we induce it with carbon monoxide, again, we should remember that, additionally, in our body, we have a limitation of oxygen due to formation of inhibition delivery in hemoglobin. But here we can see that depolarization is much lower. And this is real oxygen glucose deprivation, and we can see as well that it's almost complete blocking of the mitochondrial respiration. So, yes, carbon monoxide can produce something on our respiration, in our endogenous respiration in mitochondria. So, how it works, and we also measure effect on the NADH level. NADH is a substrate for mitochondria, and if we stop to consume it in our mitochondria, we can see increase. And what's happened with carbon monoxide, it's definitely inhibit respiration, but not completely. It's not something which completely kills our system, what we can see in, for example, with some toxins. And it's induced only about 30-21% of the total inhibition. But if we, again, come back to the hypoxic and anoxic conditions in the brain, we can, again, see the level of the oxygen which might be toxic for the tissue, But what is important that ischemia or anoxia induce endogenous production of reactive oxygen species. What is generally our oxygen is toxic by itself, and we live in this environment. But in some conditions, it's changed and it can produced by our cells in specific enzymatic reaction, or by mitochondria, or by radiation. Well, it might be exogenous production of all this reactive oxygen species. And finally, it's induced to oxidative damage and death of neurons and astrocytes, cells which support neurons in the brain. Effect of carbon monoxide, which was released in our case from special compound COM41, we can see that it induced massive production of reactive oxygen species in neurons and all the supporting cells. Well, it sounds pretty messy, but if we just separate neuron from those traces, we can see increase of reactive oxygen species production in time of the CO exposure. But what is important that the major production of the reactive oxygen species, which is, I would say, extremely and high, and to be honest, I haven't seen in my experience such a high production of the free radicals in cells. It's happened in the time of reoxygenation. And what is important that, again, it's not, we need to understand what is the source of all this overproduction of reactive oxygen species. And we try to understand, we try to see if it's mitochondria, it's possibly mitochondria, and we use specific antioxidants which is allocated in mitochondria, this is mitotempa, and we realize that it's partially produced in mitochondria, but only partially, because the major ROS production happened in the later event. And we found that it's mostly produced by enzyme which is first been identified in phagocytes. It's enzyme called NADPH oxidase, and and can be blocked. Again, blocked just in the end point. When in the time of reoxygenation, and we can see that this inhibitor blocked it almost completely. So we identify enzyme which is responsible for toxic ROS production in the time of reoxygenation. But this is always question, because free radicals and reactive oxygen species produce in physiology and worked as signaling molecules and can be different in the different brain regions. So we can talk about oxidative damage just when it's induced damage of lipids or reduce our endogenous antioxidant level. And here, we try to estimate it, using a specific fluorescent indicator for lipid peroxidation, and we found, yes, we have a massive oxidation of our lipids in the time of the carbon monoxide exposure, and specifically in time of reoxygenation. And it can be significantly reduced using various inhibitors, with most pronounced effect of inhibitor of NADPH oxidase. This is when we start to think about some therapeutic implication, for example, in the time of well, if we talk about lipids, it's a very sophisticated system, but, we can replace the lipids with different omega-3, omega-6, or inhibit specific enzymes, or antioxidants, and all the strategy being tested in many other processes, including, for treatment of potential treatment of neurodegenerative disorders with actually no success, specifically when we talk about antioxidants. And another problem, we have to remove images, but I'd like to say that carbon monoxide significantly reduce the level of endogenous antioxidant in our brain. That strongly suggests oxidative damage and that we have oxidative stress in these cells. And again, we can recover this situation using inhibitor of the enzyme which overproduce free radicals in the time of reoxygenation. And of all what I said before, it was mostly mechanism and how we can block the different points in the time of the carbon monoxide exposure and reoxygenation. But, how it's related to pathology generally, and how it's related to cell death. If we treat cells with carbon monoxide for 40 minutes with recovery, we find pretty high level of the cell death just next day. 24 hours after. And if we pretreat cells again with with various inhibitors and antioxidant, we can see that the most profound will be inhibition of the enzyme which is responsible for this overproduction of the reactive oxygen species in the time of reoxygenation, which is generally quite optimistic, because if we had something which happened just before, we could not potentially treat the neurons or whatever. That means we can potentially affect toxicity before we start reoxygenation of the, at least, we can talk about neurons, but of course we can talk about people who've been exposed to carbon monoxide. And this work, of course, it's been done in the Queen Square Institute of Neurology, and of course, it's with co-investigator Plamena Angelova, and of course, Isabella will just introduce us to this exciting field and important field. And of course, this work would not be done without support from CO Research Trust. Yes, thank you.
Okay, thank you. I'm going to follow the lead of Shirley and ask if anybody has any questions most immediately for Andre. Yes, the microphone's coming. Andre, thank you.
Thank you.
Hi. In view of the reduction in glutathione levels that you've identified in a setting of monoxide exposure, do you think there could be a therapeutic role for administering N-acetylcysteine?
I would say probably yes, but at the same time, we don't know because we haven't seen any inhibition of the production, of course, glutathione. It's more looks like, it's reduction due to high production of the reactive oxygen species. Yes, it might have effect. How big effect? I cannot expect. We just spoke about this. But anyway, yeah, thank you. It's a good idea. Yes.
Yep.
Hello. I've got two questions, sorry, I'm a bit greedy. The first one, looking at those graphs, you seem to have an increase in reactive oxygen after you stop the carbon monoxide exposure. What do you think the mechanism is for that?
Yes, it's what I mentioned, well, of course, we have increase and massive increase, specifically, specifically here. Well, it's because this is, the measurement of the free radicals is just, it's constant oxidation, and you can see that it's massive in the time of carbon monoxide exposure, but the most profound is in the time of reoxygenation. And this is, the mechanism is simple, it's just NADPH oxidase, which we just show with inhibitors, and of course, not only one, but it's how it works.
So leading on from that, do you think administering oxygen could make that worse?
I'm not just thinking, it is, and the most, let's say most of the cells, at least neurons in this situation, die not because of carbon monoxide exposure, they die because of the reintroduction of the oxygen. And because, all carbon monoxide stimulate activation of all these enzymes, but because of limit of oxygen, because of some other factors, they cannot work in the full rate. And then oxygen is reintroduced. It's just produced, as I said, I've never seen such a high level of ROS production. And that's why if we block, this part, we can at least, significantly reduce the risk of the cell death.
Thank you.
Andre, thank you. I'm sure I certainly have a few more bits for next panel session. But thank you very much, Andre. Right. So I hope everybody's clicked on the point that by delivering the treatment that we've used for the past 150 years, we've seen that there's an issue. And not only is there an issue, but Andre is delving into ways to sort that out. So I think this is a very exciting piece of research that has really going to probably be a game changer on the treatment side. And obviously it's lovely to be able to explore that in this session and going forward into the sandpit tomorrow. So Andre and Plimena at the back, thank you very much indeed for that. But moving nicely on to this, anybody who didn't catch the last bits. We're going to move on to Dr. Robert Dickinson, who has been determining the biological effects of repeated low exposure to carbon monoxide. And this moves on really nicely from Andre's because it takes us further than the treatment. It's what happens next. And Robert's research interests are in understanding the pathophysiology of acquired brain injuries, such as brain trauma, ischemic stroke, and now carbon monoxide toxicity. And his lab uses a variety of techniques to understand the underlying mechanisms of brain injury and to evaluate potential new treatments. And what we'll see from him is almost like an understanding of why we've seen what Andre has worked on and then taken further. And also, this will then influence what might happen further down the line again, and that's where Steve is going to very neatly come into the session. So we're doing a rather lovely story in this session, but I'm going to now hand over to Robert, who is going to join us by video link.
Well, I'd like to thank the organisers for the opportunity to present here today. So why is research on repeated CO exposure and biomarkers required? Well, in the UK, the number of acute exposures to CO is around 4,000 per year, and there are up to 30 deaths. However, the number of lower level and undiagnosed cases of CO exposure is unknown, and it's likely to be many-fold more. Indeed, a UK study showed that up to 4% of all patients presenting in A&E with non-specific symptoms had elevated carboxyhemoglobin. And the effects of repeated low-level exposure are not well studied. Also, the mechanisms underlying the neurological sequelae of CO toxicity are not well understood. Carboxyhemoglobin is not an ideal biomarker, it's not persistent, and it has poor signal to noise at low CO levels. And there are limited treatments for CO poisoning, currently limited to the administration of oxygen, either at atmospheric pressure or under hyperbaric conditions. However, it is known that there are persistent neurological symptoms associated with acute CO toxicity. And these include memory and cognition deficits, problems with motor function, and depression and anxiety. The mechanism of CO toxicity, as I said, is not fully understood. Something that is understood is that CO binds tightly to hemoglobin, and it reduces its oxygen carrying capacity. And the most sensitive organs to the hypoxia are the brain and the heart because of their high oxygen demand. However, CO toxicity is now known to be much more than just hypoxia. This is a complicated diagram. I don't expect to take in all the details, but just to highlight, in yellow, this is the binding to hemoglobin and the hypoxic effects. But as you can see, there are a large number of other things that CO is now known to do. And it's known that CO has direct effects on mitochondria and affects inflammatory pathways. So why do we need preclinical research? And by preclinical research, here I'm referring to animal studies, which are the gold standard in preclinical research, using rodents, rats, and mice. They're the most widely used in basic research and in the pharma industry. And they have behavioral outcomes that are well characterized in models of other types of brain injury, such as stroke and traumatic brain injury. Complex cognitive and behavioral outcomes are observable in rodents. And one of the key things about an animal study is you can include identical control groups, and you can test after exposure to precise known concentrations of CO. And you can also evaluate the efficacy of novel treatments. And they can also be used for biomarker identification. So what are we trying to model? We're trying to model a scenario where, for example, someone is coming home each day from work, and in their house they have a faulty heating appliance, which is exposing them to a low subacute level of CO, and they're being exposed to that perhaps over the duration of 5 to 7 days. Something else that's becoming of increasing concern is environmental exposure to CO and other pollutants, for example, from traffic, particularly in cities where you might have schools that are located near busy roads. So in our animal model, we have a chamber here where we can expose a number of rats to a known concentration of CO, and we expose them for 2 hours a day, and we repeated the exposure over 5 consecutive days. And we look at a number of outcomes, behavioral outcomes, histological outcomes, MRI, and we're also looking at biofluid biomarkers. Just to explain some of the tests that we use. We can examine locomotor function by using this device called the catwalk, where the rats walk along this walkway here, and with a video camera below, we can visualize their paw prints, and you could calculate a number of gait parameters from the computer analysis of the videos. We can measure learning and memory by using this paradigm called the Barnes maze, which is a circular table. And in one of the 4 quadrants, there will be this escape box, and the animal has to find the escape box. And we can see whether or not the animal will remember where the escape box is. And again, this is videoed, and we analyze the resulting videos. We can look at anxiety using this paradigm called the elevated plus maze, which has 2 closed or dark arms and 2 open arms. And rodents such as rats and mice are nocturnal animals, and so they'll prefer to be in the closed arms, and the number of times that they would enter the open arms would be a measure of them feeling less anxious. If they feel very anxious, they'll spend more time in the closed arms. Another outcome that we can look at the end of the experiment is we can take the rats' brains and we can section these, and then we can stain them with markers for different cell types. Shown down here in red are neurons, and in purple are astrocytes, which are a type of glial cell. And we can also look at MRI imaging. This is an example from a human brain of a CO poisoning patient. And you can see here lesions in an area of the brain called basal ganglia. We're fortunate enough at Imperial to have access to a small animal MRI scanner for rats and mice. And I'm now going to just discuss some of our preliminary findings. So our preliminary analysis of some of the locomotor parameters, there are very many of these, but at the moment we've just looked at locomotor speed and cadence, and we actually found that there was not a significant difference between the sham exposed group and the CO group in the locomotor speed or the individual limb speed. When we looked at the memory paradigm using the Barnes maze, so this is the goal box is located in each of the different 4 quadrants, and then the heat map here, the brighter the color indicating more time spent in a particular quadrant. And we can see that in all cases, in each of the quadrants, both the sham group and the CO group spent more time in the quadrant where the goal box was in that occasion, indicating that there was not a memory impairment at that time point. And so we can then quantify that by looking at the time spent in the target quadrant and the time spent in the goal box area. If we looked at the anxiety in the Barnes maze paradigm, again, we get a heat map, and it spends most of the time in the closed arms, but there is some time spent in the open arm. As I say, the more time it spends in the open arm, the less anxious the animal is. And although this didn't reach significance, we did see evidence of anxiety in the CO group. For example, the sham group enters the open arm about twice as many times as the CO exposed group. And the total time spent in the open arm is about 5 times less in the CO group. That's indicating that the CO group is showing signs that it has anxiety. When we looked at the MRI scans, we found changes in this area here, the globus pallidus, which is part of the basal ganglia, which is the area that was known to be affected in human CO poisoning. And we saw changes in diffusion tensor imaging parameters that indicates alterations in the brain microstructure in that area. The ongoing work is we're doing further analysis of these preliminary MRI data. We're also doing histological analysis of the brains, and we have 30 of these rat brains to analyze. And we're also looking in the blood and urine samples for biomarkers. Ongoing things that we plan to do is look at later time points to see whether there is a delay in the onset of impairments, and look at longer, perhaps chronic exposure paradigms. And also, we hope to evaluate novel treatments. Just as a taster of the sorts of things that we might evaluate as a treatment, this is a recent study on another type of brain injury, traumatic brain injury in rats, and we've been evaluating the inert gas xenon as a potential treatment. And we found in the traumatic brain injury paradigm that the controlled TBI animals had a reduction in their locomotor speed in the catwalk, and that was prevented by the xenon treatment. We also saw that the TBI control animals, compared to the sham animals, they had neurodegeneration in the hippocampus, which is associated with learning and memory, and that was prevented by the xenon treatment. Also in the in the hypothalamus, which is one of the things it does is regulate the sleep wake cycle, and we saw a loss of neurons in the TBI control, and again that was prevented by the xenon treatment. When we looked at the glial cell response, we found that xenon seems to potentiate the action of, or the number of resting or helpful microglia, and we think that perhaps this is one of the ways in which xenon has its neuroprotective effect by potentiating the action of these helpful microglial cells. So just to summarize the presentation, this is a multi-stranded study of CO in rodents. We're looking at various outcomes, behavior, histology, and MRI. We're also hoping to identify novel biomarkers, and with the aim of establishing a mechanistic connection between CO exposure and long-term neurological impairments. This has been the work of a large team of people at Imperial College. I'd like to highlight Philip Aitken, Georgina Carson, and Amina Hamid, who played key roles in the CO experiments. And I'd also like to thank our funders, the CO Research Trust, and before that, in their previous incarnation, the Gas Safety Trust, also the MRC, who supported the lab for a number of years. And thank you also to Kane Instruments, who supplied the CO monitors that we used in our animal experiments. So thank you very much for your attention, and I'm very happy to take questions.
So as you probably realise, Robert isn't here to take his questions, unfortunately. But he has said if you would, I'll just move it on, if you would like to submit questions to the CO Research Trust, whose email is at the bottom here, specifically for Robert, he will be more than happy to get back to you and answer them. So thank you. Another step in terms of CO Research, again funded by CO Research Trust. As you'll notice from Robert's last slide, it's been a long process because his funding started whilst the CO Research Trust was still the Gas Safety Trust. And these things do take time, but it really did show how we can use techniques that are fairly mainstream in some areas, but have not been utilised at all in terms of carbon monoxide. So this is a very exciting time in terms of scientific development and understanding for carbon monoxide, not using necessarily anything that is particularly novel or experimental in terms of the method used. However, what Robert has done very nicely, as I mentioned before, is essentially introduce our third speaker of today, Dr. Stephen White, who is studied physiology and philosophy at Oxford University before undertaking a doctorate in neuropsychology. He went on to qualify in medicine at Cambridge University and trained in psychiatry and neuropsychiatry at the Maudsley Hospital in London, and also in the United States. He moved to his current field of clinical neurophysiology and epilepsy after EEG epilepsy fellowships in the US at the Medical College of Virginia and the National Institutes of Health. Dr. Stephen White is now in independent practice in clinical neurophysiology at the Cromwell Hospital and the Portland Hospital for Women and Children. And since 2017, he has worked in the NHS at the National Hospital for Neurology and Neurosurgery. He maintains his long-standing interest in the neurobehavioral effects of encephalitis, traumatic brain injury, and carbon monoxide exposure. I'm going to add one thing to that, and that is that Dr. White is also a member of our COMED group, the subgroup of the All-Party Parliamentary Group, and leads with another colleague on the neuropsychiatric side of things. So, Dr. White, over to you.
Well, thank you very much for the invitation to speak. This is going to be a rather different and much lower key presentation. I don't have any data and I'm not a scientist, but I just wanted to pause and comment on how what we've heard so far can intersect with clinical medicine on a daily basis. My own involvement in carbon monoxide was in the context of what Isabella described. I ran for a number of years an epilepsy clinic at Charing Cross and St Mary's hospitals, and I had, because of the background described, an interest in the neurobehavioral aspects of those disorders, and by rather circuitous reasons, I began to see a small number of people who'd been exposed to carbon monoxide and had problems following that in the context of that clinic. So I'm giving a perspective really from a daily clinical context. So I'm going to speak about the neurobehavioral and neuropsychological consequences of carbon monoxide exposure on the brain, which are clearly important in daily practice and in terms of health service provision. I think with education, people are now beginning to realize that carbon monoxide is lethal, and we read in the newspapers and the media about fatalities from time to time from carbon monoxide, so people understand that. But I think there's little understanding of the fact that if you aren't killed by carbon monoxide but are exposed to it, it's not necessarily the case that you will be fine subsequently, or that you will recover quickly from the effects of it. And unfortunately, this lack of understanding of the true possibilities of exposure to carbon monoxide is endemic in the medical population as well as in the general public. Because there's nothing novel about what we're saying in relation to the adverse effects of carbon monoxide. This paper is from 20 years ago, and even then was emphasizing that carbon monoxide is dangerous and that it can indeed produce long-term permanent neurological defects. There's a lot of information of various sorts about the effects of carbon monoxide on the brain. We can't review this in any detail, but the three areas are really those that there's a small amount of experimental evidence going back many years with a number of studies in which healthy volunteers were exposed to low or medium levels of carbon monoxide for fairly short periods of time, and then given formal psychological testing to look at cognitive function. And these have shown that even quite low-level brief exposure that doesn't really produce much in the way of overt symptomatology at the time can be associated with what is hoped, at least, is a transient effect on cognition in various domains of testing. And that's well established. The bulk of our information comes from a very messy medical literature which is largely composed or comprised of individual case studies, often in detail, and small groups of patients, with a certain amount of work mainly from the United States, from a neuropsychology context in which larger groups of patients were looked at more systematically with batteries of neuropsychological tests. And what we're missing is any kind of very satisfactory long-term systematic evaluation of what happens to people, particularly after low-level exposure to carbon monoxide. We know that it produces a problem, but we don't know much about the natural history, and a lot of the information we have is anecdotal, although that's, of course, how physicians understand conditions by the patients they've seen in their own experience. And finally, there are occasional natural disasters in which largish groups of people are exposed to carbon monoxide in a particular event. And there are a number of studies looking at what happens to people who've been exposed to carbon monoxide in that way. As an example of the natural history, everyday clinical information about carbon monoxide, this is a recent example. In the days of webinars, we're able to look at the Harvard School of Public Health Grand Rounds, which had recently a very nice, interesting case here, which is very representative of what's in the general clinical literature of a husband and wife who spent some days in a hotel, didn't feel all that well and thought they might be coming down with the virus, and then clearly there was something more seriously wrong as they began to get brain fog and cognitive impairment, and it transpired that they had indeed been exposed to carbon monoxide in the hotel over a period of several days. And the main point of this slide is really that, unfortunately, the answer to the question in the title of the Grand Rounds is yes. They were seen about sort of 6 or 8 months after their exposure, and it was indeed the case that they were still sick from carbon monoxide poisoning. And we now recognize that persistent or permanent problems following carbon monoxide exposure is common. And as an example of the natural disaster literature, this is a description of Storm Klaus, which was a very bad winter storm in southwest France in 2014, which left a large portion of the population of the region without power. And of course, people responded in the way that you would predict. They got all kinds of portable generators out of the garage and old kerosene heaters to give themselves power and heat, which led, unfortunately, predictably, to a significant number of people coming to hospital with carbon monoxide exposure over a period of a few days. And the local psychology department evaluated a handful of these people, I think only about 30 or 40, a couple of months after exposure to see how they were doing then, and gave them a battery of formal neuropsychological tests looking at cognitive function. And unfortunately, they found at that stage, when the common assumption would be that they should be okay, they showed significant impairments in a number of different cognitive domains on formal testing, as well as increased ratings on depression scores. It happened to be the case that they had some initial COHB readings in those patients, and they did find a negative correlation with the cognitive test performance, although that's, as we've heard, is not something which is reliably reproducible. So that's really discussing acute exposure over a period of hours or days to carbon monoxide. But as we've heard, the thing that's come to light more recently is the problem with chronic low-level exposure over extended periods of time of months or years. And as this review indicates, it's unfortunately become apparent that even if you remove people from the source of their poisoning, they do not necessarily return to normal or baseline neurological function. So it's clear that even low-level chronic exposure often in a domestic or employment setting, can lead to permanent problems from a neurological perspective. So I think it's very clear from clinical experience and from the literature that significant exposure to carbon monoxide can produce an acquired brain injury. And I think we need to consider the problems following carbon monoxide in that way, in exactly the same way as we do consider traumatic brain injury or encephalitis or other causes of acquired brain injury, because the symptomatology and the consequences for people are exactly the same. I think part of the problem is that it's not really been widely recognized as a cause of acquired brain injury in quite the same way, certainly not by the general public or the general medical community. This is a slide from the Encephalitis Society that makes the point that in people who've sustained an acquired brain injury, often there are many domains which are affected, both cognitive, neurobehavioral, as well as more general things like problems with balance and coordination and fatigue. And indeed, if you speak to people with acquired brain injury of various types, fatigue is often a central complaint. But this is not really emphasized sufficiently, I don't think, because neurologists don't really understand why people who've had an acquired brain injury develop such problems with fatigue, and they don't really have much in their repertoire to deal with it, so it tends to get put to one side. So cognitive function is affected, as we've heard, by carbon monoxide exposure, and you will typically see, although there's not a specific pattern related to carbon monoxide poisoning, you will usually see problems in a number of different domains, almost invariably in memory and concentration, but also with carbon monoxide in things such as speech and language. This is, if you speak to people who've been exposed to carbon monoxide, you'll often find a characteristic description of word-finding difficulties, hesitancy in speech, and difficulty writing, as well as I mentioned, fatigability. So a number of different cognitive domains are affected in just the same way as with traumatic brain injury or encephalitis. There have actually now been a large number of neuroimaging studies of people who've been exposed to carbon monoxide, which gives some understanding of why the particular pattern of problems can arise. And it's become very clear that on imaging, you see a combination of both very localized changes in particular brain regions, but also of more diffuse changes in the brain. So, for example, there was one study that showed the hippocampus, which is down here at the bottom of the slide, shows atrophy and loss of volume following carbon monoxide exposure, and that this persists. And the hippocampus is critically involved in memory function. And this explains or makes understandable why people with carbon monoxide exposure will tend to have problems with memory function. But at the same time, diffusion tensor imaging of large white matter fiber tracts which connect different regions of the cerebral cortex showed that those were also affected, which impairs connectivity of different brain regions. And this is exactly the same as is seen in people with traumatic brain injury, where it's well established that white matter tract disturbance underlies a range of cognitive and behavioral problems. I've mentioned particularly cognitive changes, but equally neuropsychiatric changes are important following carbon monoxide exposure. As with other forms of acquired brain injury, depression and anxiety are extremely common following carbon monoxide exposure. In acquired brain injury, depression and anxiety have perhaps a slightly more complex etiology, or in that clearly people who've been affected by an injury or accident of some kind and whose daily life has been affected by this will tend to be depressed and anxious about their situation for understandable psychological reasons. But there seems to be more to it than that, in that it's clear that some of the mood disturbance and anxiety is related to damage to areas of the brain involved in the modulation of mood, such as the limbic system involving the hippocampus, which I mentioned a moment ago. So it's a mixture of psychological response and organic underpinning. In the bottom of the slide, there's a constellation of disturbances of social behavior and personality. And of course, we are a complex social species. And in exactly the same way as we have physiological homeostasis for blood pressure and temperature tolerance, we have a very clear social homeostasis. So the range of behaviors which is adaptable and acceptable is actually quite limited. And people who begin to behave in ways which go beyond that will very quickly encounter difficulties. And it was very clear from work done in the 1980s in Glasgow in patients with traumatic brain injury that it's often these problems with social behavior that are the main impediment to reintegration in society. You can understand how easily it would interfere with the return to employment and how it can quickly interfere with family relationships. And the Glasgow group found that families seemed to be able to cope with this for about 2 years after the head injury, and then things began to break down when the family realized that this was the permanent state and hopes of recovery were fading. So this is an important dimension of acquired brain injury. This is from the Encephalitis Society journal, and this is from somebody who's had encephalitis. And it really highlights it very clearly in a couple of sentences the predicament that people who've sustained an acquired brain injury, whether from carbon monoxide exposure or other causes, the predicament which they face, in that most people after a mild acquired brain injury will appear normal, so to other people they will look normal. And so unfortunately the assumption is if you look normal, you are normal and you should be behaving normally. So the tolerance for somebody who looks normal behave in a way which is not entirely normal within society is very low. And I think, as this lady describes, the predicament which people with mild acquired brain injury face is very much that. So on the final slide, in the final couple of points, the question then is where do we stand with this? I think the problem, as we've heard already, is that there's very little recognition of these problems following carbon monoxide exposure, and there's, in the UK at least, there's virtually no provision for that. Specialist neuro rehab units will see occasional patients who've had very severe carbon monoxide poisoning and hypoxic injury. But for people of the kind we're really discussing today, people who have persistent mild to moderate cognitive and neurobehavioral changes following carbon monoxide exposure, currently there's essentially nothing in the UK at all. Occasional patients will get themselves referred to a neurologist, but the general neurological examination will be normal, the MRI scan is normal, neuropsychology testing may show a few problems, but nothing that they get their teeth into, and they are discharged or referred to psychiatry because of the depression and anxiety symptoms. But fortunately, the one positive is that there is now in the UK a model for clinics to support people with exactly this kind of problem in a different context. So there are a number of specialist traumatic brain injury clinics, a local one being at St Mary's Hospital in Imperial, where at Imperial, under the direction of Professor David Sharp, they have developed a multidisciplinary team, and they have a Monday morning clinic where they see patients following mild to moderate traumatic brain injury, and the neurologist leads the clinic, but they have a neuropsychiatrist who sees patients from the psychiatric perspective, and neuropsychologists who deal with primarily with the cognitive changes, and also access to imaging and other facilities such as speech and language therapy if needed. And because the profile of problems following carbon monoxide exposure is very similar to what we see after traumatic brain injury, this really gives an excellent model for what could be done for patients with carbon monoxide exposure. And we've been discussing this at some of our meetings over the last few years, and I think we are beginning to get traction with the idea that we need to develop services in this way for people specifically with carbon monoxide exposure in exactly the same ways as with traumatic brain injury. And we're not quite there yet, but I think we are heading in that direction. I think a carbon monoxide clinic will not spring up out of the air overnight. I think the way clinics in neurology develop is that it's likely that in the way I was doing in my epilepsy clinic at Charing Cross, people will begin to see some patients with carbon monoxide exposure in the context of another specialist neurology clinic, and that it will then develop into a special service. And the final word, in the epilepsy world, which was my main field, epilepsy nurse specialists, epilepsy nurse practitioners are a key role, and they will run clinics alongside neurologists, and in between clinics will act as a contact point for patients who have problems and need further advice. And I think the world of carbon monoxide exposure, it would be ideal for developing that role. So I think we are not there yet, but I think we're at least beginning to recognize that we need to develop specialist facilities to support people who have problems following mild and moderate CO exposure. Okay, thank you. Yes.
Stephen, thank you very much. I don't want to take up the time with me talking. Adrian's made sure that I shouldn't do this. We have 5 minutes for some panel questions, but I would like to say just a few words in terms of this session. I think really bringing an element of hope that we haven't actually seen before for a long time with carbon monoxide. Despite significant change to our thinking regarding treatment using oxygen therapy, this obviously has implications for the ambulance setting and the in-hospital setting, and it's important to carry this through to understanding and providing a treatment that reduces neuronal injury. And from Robert's study, his study was very important in terms of it mapping the exposure that we saw in the indoor environment, people going to work. But of course, our model of behavior has changed. We're at home now. We work much more at home. So what are the implications? How would we look at his study now in terms of your exposure, and what might he see? We have the information from Steve regarding bringing to light the case studies, but also indicating that we do have a network out there in terms of the TBI clinics that, from Heather's study, we know, we'd never get a clinic just for CO based on the numbers at the moment, but, we should look at maybe integrating these, the CO into these clinics. And going really right back to the beginning where Sharon spoke of the need for support for victims, this is what treatment and therapeutics is all about. From the moment somebody is poisoned, we're there to improve that person's life. Even if somebody's well-being cannot be seen because they're covering up and they're trying to cope, this needs to be. We need to support these people and help them as far as possible to return to their normal, not what we might perceive as normal. And thank you. I would like to now open up the floor for questions to our panel. Laura.
Thank you so much. Really interesting panel. I'll make it quick because I don't want to dominate the conversation, but I just know that Sharon has been doing some really interesting work on treatments and therapeutics as well, in terms of some of the more lifestyle things that individuals can look at doing. So I don't know if you might want to nominate you to talk about that a tiny bit, Sharon, if that's possible.
Thank you, Laura, for putting me on the spot. Just anecdotally, we understand that carbon monoxide poisoning survivors become very sensitive to carbon monoxide, explaining the reason why some people have no effects and other people have significant effects at the same level. So we provide wearable carbon monoxide detectors that go down to zero to carbon monoxide poisoning survivors so that they can avoid CO at all costs, helping with their recovery. I don't want to take up, all the 5 minutes.
But you feel from feedback, you feel that this helps them mentally to cope better?
Not mentally, but physiologically.
Okay.
Just from my own experience in recovery,
Mm-hmm.
I would track very specifically everything in my day,
Mm-hmm.
and was not ever able to correlate regression in my recovery to any specific thing until I started wearing a carbon monoxide meter, and then I could specifically correlate a setback to a carbon monoxide exposure.
Okay, so in that regard, Steve, with your experience in the in clinics, where would an intervention such as wearing a monitor, would that come into it at all?
Yes, I mean, I think this it relates to a wider neurological point in that in the traumatic brain injury world. The concept of a second injury has been much written about, so that it does seem if people have had an initial traumatic brain injury, that they become more susceptible to subsequent brain injuries, and that this, in its most obvious form, is apparent in boxing, for example. But I think the same principle about brain function is likely to apply, that, as you say, that if the brain has been affected by carbon monoxide, subsequent exposures to carbon monoxide may have a deleterious effect. And you're right that there may be a greater sensitivity to lower levels of carbon monoxide, which wouldn't necessarily produce a major effect on somebody else. So I think that's important, and I think in this country completely unrecognised, because I think there's nothing remotely corresponding to that. I think we just haven't reached that level of thinking here about what happens if you then go back to repeated carbon monoxide exposure after a known event.
Thank you.
So I think that's a very important thing to recognise.
Yeah. Stephanie?
Hello. I found the talks very interesting, and I agree with you, Izzy. It may be at last there's some hope, which would be absolutely brilliant, because that's been the problem, of course. We've not been able to offer anything. My name is Stephanie Trotter. I run a charity, CO Gas Safety, and I've been talking to survivors and victims, whichever they prefer to be called, and family members for 27 and a half years. And I have a lot of anecdotal reports to make. I would agree with Sharon that they become hypersensitive, and it's very difficult again to link it because of monitoring it. And I also have noticed that they react to drugs and x-rays very, very badly and unpredictably. And this seems to be something that is not known amongst the medical profession. Maybe it is. But again, it's purely anecdotal, but it happens to nearly every person, I'd say, who's been badly affected. So thank you.
Definitely, thank you. And Emma, sorry.
Hi, Emma Fraser from London Fire Brigade. I just had a question. It might have been answered, so forgive me if it's a silly question. Is there much work around diagnosis and therefore treatment retrospectively? So we're talking about numbers that are quite identifying numbers of those who have been exposed to CO at different levels. Is there anything going forward? So someone might present to you with a neurological condition but then actually it was thought that it was one thing, and then going forward actually we find out that they had exposure to carbon monoxide, and how do we then, is there a treatment going forward for that, or is that something that it's too late then?
Yeah, no, I understand what you mean. I think, yes, the answer to the first question is yes, that people obviously don't necessarily come to the clinic with a diagnosis. They come with symptomatology, so they will maybe be describing mood disturbance, memory impairment, and so on, and it's not clear what the problem is. So somebody who's been suffering in that way may well, it's certainly perfectly possible that they will prove to have had carbon monoxide exposure. Of course, it would be important to distinguish, have they had a poisoning event in the past which has led to problems which have persisted now, or the more urgent situation, are they having problems now because they're currently being exposed chronically to. So there are many strands. But the answer to the question is yes, it certainly could be the case. I think the problem, I'm not by any stretch of the imagination a toxicologist or a scientist of any sort, but one of the problems clinically is establishing the diagnosis retrospectively. So if somebody was exposed to carbon monoxide 18 months ago, unless that was documented at the time, it may be hard to establish, except, of course, historically, in the sense of by establishing more information about what happened. So, for example, one of the people I saw who was perfectly happy for me to talk about his experience, he was a PhD scientist who was very analytical about what had happened to him and kept very clear records. And he was poisoned after his boiler was serviced incorrectly over the course of about a week. And because he was a scientist and he felt well, and then he had brain fog, he thought this isn't right, and he worked out what was wrong with himself. Now, had he not done that, his diagnosis mightn't have come to light. So I think if we can elicit a history of a definite exposure, like if they'd been in one of these storms where people were using generators and so on, it may be possible to retrospectively establish it, but without a clear history, the difficulty is because of the lack of biomarkers of previous exposure. In terms of intervention, sort of two things very briefly. In acquired brain injury, in general, the general principles of support and rehabilitation and memory support are fairly sort of generic across different causes of brain injury. And so the principles would be the same, and they're largely supportive. They're practical, but they're not what you would necessarily call a treatment. There was discussion, of course, which we won't be able to go into today, about hyperbaric oxygen therapy, clearly in the acute phase, but there's a hugely messy and controversial literature suggesting that if people were given hyperbaric oxygen at a later stage, it might help symptoms. I think that's not really widely accepted. The experience of my PhD scientist chap was that he, when he was still having symptoms about a month, 6 weeks after he'd been exposed, he managed to get him, he researched it further, and he got himself an MRI, saw a neurologist, and he got, he had, I think, about 11 sessions of hyperbaric oxygen. So this, we're talking about a couple of months after exposure, when he was still symptomatic. His own experience, for what it's worth, was that he felt that it did help him initially, but after the first 4 or 5 sessions, there was no further benefit, and he had a sense that he was actually being made worse by it. So I think the two questions and two different answers. But I think at the moment, in terms of treatment, in the sense that we normally use that word, we're lacking treatment once we've gone past the first few hours.
Right, I'm going to have to end the discussion, and I know we could go on. I have loads of things written down, which we'll have to discuss during the lunch break. But again, thank you very much to our speakers, and I think we've understood why COHB doesn't help, because there's a lot of stuff going on during treatment as well, and there's a lot more to take forward from that. So again, just thank you very much to you both, and lunch is for an hour. Lunch is for an hour, and I will let Rob Chilcott bring you all back to your places. But thank you very much, and thank you for a great, really wonderful morning session.